So another scientist, J.J. Thomson, and this was back in the early 1900s, discovered a smaller particle than the atom. So the atom is the smallest particle that has properties of the element, but the atom itself is made up of smaller particles. And I'm not going to quiz you on these guys' names, by the way. So the electron is part of the atom. It has a negative charge. It's much smaller and lighter than the atom itself. It would have to be smaller, otherwise it couldn't be in there, right? And it is present in many different kinds of substances. So they found that this was a fundamental particle. It wasn't just that gold atoms had electrons, but every element that they looked at had electrons. So that was pretty interesting. So he proposed, these were, he made some observation, and then he proposed a hypothesis, and he proposed that atoms must have some positive charge that would balance out that negative charge. He predicted that, because they knew that the atom itself was neutral. It didn't have a charge on it. If it's got negative particles in it, then it must have some positive particles also. And his idea of how the atom was put together is called the plum pudding model. Doesn't make a lot of sense to us. Anybody here ever had plum pudding? No, I haven't either. It's a British dish, and it's really, the closest thing we have would be like a blueberry muffin. So it's a bread-like thing with plums spotted throughout. So think of a blueberry muffin. We'll call it the blueberry muffin model. So the negative electrons are like the blueberries in the blueberry muffin, and the bread part is just the rest of the atom, and that's got a positive charge. And this was his proposal, his hypothesis about the structure of the atom. So one of his students, Rutherford, set out to test this hypothesis. And he actually wasn't setting out to disprove it, he was trying to confirm it. But he did this experiment, the gold foil experiment, in 1909. My husband had the opportunity last summer, not just this past summer, to go to England and tour some of these science labs. And he was able to look at John Dalton's actual notebook. They've saved all this stuff. It was really cool. And so a lot of this history is in England, and you can actually go, and they have, really cool museums and everything. So if you ever get a chance, you should go see it. So this experiment, what did he do? Well, he took this, a little particle source here, and we don't really care what kind of particles they are. Little tiny, tiny particles, smaller, well, on the size of small atoms. And he shot them at this piece of gold foil, really, really thin piece of gold foil. And this blue circle around here is a detector that detects those particles. So when the particles hit, it makes a little tiny flash of light, and so you can see where the particles went. So they've got this beam of particles going at this piece of foil. And most of the particles went straight through. Some of them bent a little bit. What was really shocking is that some of them bounced back. So here's an illustration. So this is the plum pudding or blueberry muffin model. So you've got all this bread here, the purple stuff, and these little electrons. And what they expected to happen was that these alpha particles, these little tiny particles, would just go straight through. And indeed, most of them did. But some of them bounced back. Rutherford said this was as shocking as if you shot a cannonball at a piece of tissue paper and it bounced off the tissue paper and hit you. That's how shocking this was to them. They could not believe this. What on earth? How did this happen? This changed the model because obviously the model's wrong. In order for those particles to bounce back, they must be hitting something that's pretty big, pretty massive. And so this led to the discovery of the atomic nucleus. The nucleus is a small little thing in the middle of the atom, and that's where almost all the mass of the atom is. So it's incredibly massive. So it's, like hitting a brick wall. It's just not moving at all. Just smash. Things are going to bounce off of it. whereas the rest of it is basically empty space and things will just pass through. So we've got this massive nucleus, and so when the particles hit the nucleus, they bounce back. If they came close to the nucleus, they would be a little bit deflected. And so this explained the observations that they had in this experiment. So this led to Rutherford's nuclear theory of the atom. Most of the atom's mass, all of its positive charge, is in the nucleus. The nucleus is incredibly dense. If you were able to, you can't, but if you were able to take nuclei and squish them together and make them the size of a period in your book, little tiny, it would weigh millions of tons. Incredibly dense. So little tiny nucleus, most of the volume of the atom, most of the volume of the atom is empty space. And in that empty space, we've got these tiny negatively charged electrons that are just kind of going around doing their thing. We'll talk more about what they do later. The number of negative charged electrons outside the nucleus is going to equal the number of positively charged particles, and those are called protons, that are inside the nucleus. So the number of positive charges has to equal the number of negative charges. So in this image here, it says the nucleus is greatly enlarged and the electrons are portrayed as little tiny particles. To give you an idea of the scale of this, if the nucleus was the size of a green pea and you put it on the 50-yard line of a football field, the edges of the atom would be at the goal lines. Little tiny pea, and the atom is as wide as the football field. And in that big space, there's a few little tiny electrons, much smaller than the little pea. And so an atom is mostly empty space.